So let me talk about logic gates, logic diagrams, and then later I'll talk about Minterms and Maxterms and some of product and product of sums. Right, let me start with logic gates and logic diagrams. So because we have the AND operator, I need to design a gate. Okay, so I need to design a circuit that acts like an AND gate. So this AND gate has the following symbol, which is shown here. This is the symbol of an AND gate. It has two inputs, X and Y, and the output is X and Y. Okay, so this is called an AND gate. So we also have an OR gate. It has two inputs, X, Y, and the output is X or Y. And I have a NOT gate, which is called an inverter. And this is the symbol of the NOT gate. It looks like a triangle, but there is a small circle or bubble appearing at its output. So this is what inverts the signal. So if the input is X, the output is X prime. So this is known as a NOT gate, or it's known as an inverter. Now these gates are physically designed using today in modern technology using transistors. So a transistor is a switch, that can be switched on or off. So think about the gate internally inside the gate. So I don't really want to go and dig deep inside the gate, but think about it as consisting of switches. Okay, so these switches, I'm showing here two switches, one for X and one for Y, because we have only two inputs. If I had a third input like Z, you can also have an AND gate with three inputs if you want. It will have three switches, X, Y, Z. Now the switches are shown in series. So by default, the switch will be open. But if you apply a high voltage, on X, then the switch will be closed. And if you apply a high voltage on Y, then the switch will be closed. So these switches are electronic switches. They are not mechanical switches. They are electronic switches. So if the input is a high voltage, and as I said, high voltage today can be around 1 volt or even less than 1 volt in modern technology. So you can control the opening. So this is not like a mechanical switch in which you use your finger to actually to switch it on or off. No, it is an electronic switch, and it is controlled by electricity. By applying a small voltage on the X input. So this will be logic 1. By applying a certain voltage on the X input, you are closing the X switch. And by applying also a voltage on the, a certain voltage level on the Y input, you will close the Y switch. Now, if both X and Y are both closed, so you must actually have X is equal to 1 and Y is equal to 1, so that you can turn on these switches and both will conduct. And basically, the electricity is going to flow through both switches or transistors. And when this happens, then basically the output will be equal to 1. So if you have a power supply here and you have some kind of a lamp or a whatever is the load that you would like to use, if you have like a bulb, for example, a light bulb, then you can turn it on. When X is equal to 1 and Y is equal to 1. So think about the AND gate as having switches which are implemented in series. If any one of these switches is open, the current will not go through, and basically the output will be 0. So this light bulb will be off. You have to have both X and Y to be both conducting. So X must be actually on and Y must be on. So therefore, both of them have to be closed switches so that the output will be equal to 1. On the other hand, the OR gate you can think about the switches are in parallel. So basically how you organize these switches, you can actually make them in series, you can make them in parallel. If you make them in parallel, it is sufficient for one of them to be closed so that the current can pass through from the power supply to the light bulb, which is shown here. So it is sufficient to have X is equal to 1 or Y is equal to 1 for the output to be equal to 1. So this is the meaning of the OR gate. So physically, it's implemented with transistors. And when you apply a voltage on the X input or a voltage on the Y input, you can turn on the switch. It will conduct, the electricity can pass through. And therefore, when the electrons pass through, they will turn on this light bulb. And therefore, you can say that the output of this OR gate will be equal to 1. So this is my OR gate, which is shown here as 2 switches in parallel. Okay, this is my AND gate, which is shown here as 2 switches, which are shown in series. Now, how about the NOT gate? Now, the NOT gate is shown as a closed transistor. So by default, if you don't apply any voltage, if you don't apply any voltage on X, so the transistor will be closed. So it's normally closed when X is equal to 0. When you apply a voltage, you are going to open the switch. So this type of switch is basically, it's a negative type of a switch. It's not like a positive type. So it will open if you apply a 1. So when you apply a certain voltage level on the X input, you will open the switch. If you open the switch, it will not really conduct electricity, and therefore the output will be 0, and this light bulb will be off. Okay, so this is the meaning, okay, of the NOT gate. So we're using a transistor here or a switch that will open when the X input is equal to 1. And it will be closed, okay, when the X input equal to 0. So when X equal to 0, the output will be equal to 1. When X is equal to 1, the output will be equal to 0. So this is the meaning of the NOT gate or the inverter. Is there any question about this? So this is really what we need to understand about gates. Okay, these are their symbols, and the technology, okay, that was implemented in the early days of computers. Okay, people use relays, and relays are mechanical switches, but they apply electricity to turn them on and off. Today, people use transistors, and these are electronic switches that are used to implement these gates. Okay, so the technology which is being used today, is what is known as the complementary metal oxide semiconductor, CMOS technology. This is the type of technology which is used to implement these transistors, and these transistors implement these gates. Now, in this course, we're going to focus at the gate level. We're going to use these logic gates to implement circuits. Okay.
Doctor, for the gate, for the NOT gate, for either way, if it's 1 or 0, it doesn't allow the electrical signal to complete circuit.
I'm not sure if I understood your question. So in the case of the OR gate, you are asking about the OR gate, right?
The NOT.
The NOT gate. So the NOT gate, okay, by default, the close is a switch. So if X is equal to 0, okay, if X is equal to 0, if you don't apply any voltage at the X input, the switch is closed. And if the switch is closed, it's going to conduct electricity. So it's going to conduct electricity from the power supply, okay, it can be like a small battery, to the output. So the output here, for example, can be a light bulb, a small light bulb, and therefore the light bulb is going to turn on when X is equal to 0. So therefore, when the input X is equal to 0, the output is 1. However, if you apply a voltage at the X input, this is going to open the switch. So the switch is normally closed when X equal to 0. And when X is equal to 1, this is going to force the switch to open, and therefore there is no current passing through, and therefore the output will be 0. The light bulb will be on. So this type of switch is going to be the opposite of the switches which are used in the AND or the OR gate. So in the CMOS technology, there are two different types of transistors. There are transistors that will conduct, okay, when their input, okay, when they use a high voltage on their input, and there are transistors that will conduct when the input is zero, okay. So when the voltage is low, they will conduct. When the voltage is high, they will not conduct. It will be like a switch which is normally closed, and it will open if you apply X is equal to 1 or a high voltage. Is this clear?
Yes, thank you.
Okay. Fine. So now we can take now, okay, the idea is we would like to use these, okay, we would like to use these gates to implement logic functions. Because later when I would like to do, for example, design a circuit, the circuit can be described by a logic function, and I can draw the logic gates for the given function. So given the following logic function, the first thing we can do is that we can draw the truth table, and then we can draw the logic diagram. Now, you don't really have to draw the truth table, but here I would like to show it to you. Now, this function f is a function of 3 variables, okay? It's a function of 3 variables. So therefore, how many entries will have in the truth table? How many entries? 8. 8, yes, 2 to the power 3 is equal to 8. So we draw the truth table, okay? So there are actually 8 entries because we have 8 possible combinations of x, y, and z. Very simple, right? So we start at 0, 0, 0, and we end up at 1, 1, 1. I can evaluate y prime or z first because this appears inside parentheses. And then I can take here x and this column here to get the final value of the function f. So you can see that for some entries in the truth table, the value of f is 0, and for some entries, it's equal to 1. So you can look at the combination here that will give you the value of f is equal to 1. Okay? So there are 3 entries in which the value of the function is equal to 1, and there are 5 entries that will give you f is equal to 0. Now that's the truth table of the function f. Okay? Now what I need to do is that I need to draw a logic diagram. Okay, so I need to use my gates. Now notice that here I have y prime. So if the inputs are x, y, z, I need an inverter, okay, here to calculate y prime. There is a prime here. Okay, I need an OR gate, okay, and I need an AND gate here. Now there is a dot here which is not really shown, but there is an AND gate here. So we need 3 things. I need an inverter, I need an OR gate, and I need an AND gate. So first you have to invert y, then you can take here the output of the inverter, which is y prime, and OR it with z. Then you can take the output of the OR gate and end it with x. So the circuit will look like this. Very simple, very easy. This is actually my inverter that's going to invert y. The output will be y prime. Then I need this OR gate that will produce y prime. Okay, let me just write it down here. So the output of this inverter here, let me just write it down. This is y prime. The output of this OR gate will be y prime or z. And now when I end it with x, it will be x and between parentheses y prime or z. Okay? So given any Boolean function, okay, you can write it as an expression. And then once you have the expression, you can draw the logic diagram, okay, for that expression. Now notice that the truth table is and the logic diagram describe the same function f. So the truth table describes the function f, and the logic diagram also describes the function f. The truth table is unique, so the values of the zeros and the ones for the function are defined uniquely by the truth table. However, the logic diagram here is not unique. Yani you can actually draw a different logic diagram for the function f. For example, I'm going to use my pen tool again. I can rewrite my function f here. Okay, I can rewrite it. Let me just write here. Sorry. Okay, as x, y prime, or x, z. Let me write z here, okay? So you can rewrite the function f as x, y prime, or xz. Now, if you write x, y prime, or xz, notice that you will need how many gates in this case? You will need how many gates?
Four.
I need an inverter to produce y prime. I need how many AND gates?
Two.
Two AND gates. And I need how many OR gates?
One.
One OR gate. So you see that this will give you a different logic diagram, but for the same function. Okay. So the function can be written differently using different expressions. Okay, this is my point here, is that there is no unique logic diagram. I'm running, where is my mouse? Yes. So there is no unique logic diagram, okay, for a given function. Okay, so the first expression x and between parentheses y prime or z has 3 literals, whereas xy prime or xz has 4 literals. And therefore it would require 2 AND gates, not just 1 AND gate. Okay, is this clear? So there can be different implementations for the same function, the same truth table, the same function. You can actually have different expressions, and you can actually have different logic diagrams for the same function. So today I would like to talk about combinational circuits. So a combinational circuit is defined as a block of logic gates. It has n inputs. Okay, so these are labeled x1, x2 up to x sub n. You can give them whatever names. And it has m outputs. So each output is a function of the input variables. So I call them function 1, f1, f2 up to f sub m. We can also give them different names. So in general, we have n inputs and we have m outputs. And each output is a function of the input variables. It could be a function of all the input variables or some of them. And each output is determined from the present combination of inputs, and this is why it's called a combinational circuit. So the combinational circuit performs operations specified by the logic gates. For example, we can design an adder that will add bits, and these bits can be the inputs, and therefore we can design the circuit using logic gates that perform this specific operation. Okay, so this is the meaning of a combinational circuit. So in this course, we are going to study how to design combinational circuits. So we're going to learn about how we can design our own combinational circuits. Given a truth table, we can design the circuit. So here's an example of a simple combinational logic. So this logic has 3 inputs, x, y, z. These are called the inputs. And we have 2 outputs, f and g. So we have 3 inputs and we have 2 outputs. Now we can write the logic expressions of f and g. Can you tell me what's the logic expression for the function f, for the output f? What is the logic expression? Anyone?
X and Y.
X and Y, yes.
Or not, or Z prime.
Or Z prime, yes. Okay, thank you very much. So we can look here at the first one, which is the function f, x and y, or z prime. Thank you. How about the function g? Can you, anyone can give me, someone else can give me the output of the function g?
X and Y,
or
yes,
or Z,
or Z and Y.
Yes, or you can see z and y or y and z. Okay, so this is the function g. So so this is a simple example of the combinational logic. Now notice that the AND gate is used, the first AND gate on top, that the output is x and y, is used by the function f and used by the function g. Okay, so you can see that xy, the term xy appears in both f and g. So here we have two outputs, f and g, and each one can be expressed by a logic expression. So if you have the combinational circuit diagram, so if the diagram is given to you and you can see the gates, you can easily write the expression for these outputs, f and g. Now, sometimes the diagram is not given to you. What is given to you is a description of the problem that you need to design, a description of the circuit that you need to design, and you might have a truth table. Only the truth table is given to you. And if the truth table is given to you, you would like to obtain, from the truth table, you would like to obtain an expression of the function phi. Of the function f, the output f. So, so the question is, if you have a truth table of a given function, how do we implement this truth table using logic gates? So how do I go from the truth table to the logic gates? Okay, is the question clear? So we want to design a circuit, okay, that implements a given truth table. I'll give you an example. Here's a truth table. Okay, so this truth table here describes a function. It's the truth table of a function f, which is a function of three variables, x, y, z. You can see that this truth table has 8 entries. And you can see that sometimes the value of the function is 0, sometimes it is 1. So it is described by this table. Okay. Now, from this table, okay, from this table, how do we obtain an expression for the function f? Because eventually what I would like to do is that I would like to design a circuit that implements this function. Okay, that's what we are after. So what is given to us is the truth table, and what I need a circuit diagram for this function. So to come up with this circuit diagram, I need an expression. So how do I do this? Any idea? Can you give me an expression for the function f?
Maybe x, z, or y.
Well, x and z or y? No, because xz here or y, maybe you are right, okay, but it's sometimes difficult to guess. So how did you come up with this xz or y?
I think it's not right because of
so here
the
y is
seventh.
equal to 1, but the function f here is 0. It's not 1, right? So the answer is incorrect. Okay, so here you have y is equal to 1, yet the function f is equal to 0. It's not equal to 1. You said xz or y. So if y is equal to 1, the function f should be equal to 1, yet here the function f is equal to 0.
What if
so it's not really that simple. Let me put it this way. It's not really that simple to obtain an expression for a given function which is defined by a truth table. So we need to work it out. We need a method that can give me an expression for the function f. Because once I have the expression, I can really implement it very easily as a circuit diagram. Do you agree? So guessing it is not going to help because you might actually guess a wrong expression for the function f. Okay?
Doctor?
So what we need is that we need a method to obtain an expression for the function f, which is defined by this truth table. In order to do this, okay, so the question is, what is the logic expression of f? This is the question. And what's the gate implementation of f? So if I have the expression, I can come up with the gate implementation. This will be easy. But how to obtain this logic expression directly from the truth table? So to answer these two questions, we need to define minterms and maxterms. So I'm going to take this function and I'm going to define what do I mean here by a minterm and what do I mean by a max term and how do I obtain a logic expression for the function f. Now this logic expression that I'm going to obtain using minterms and max terms might not be optimal and therefore it can be minimized. But I'm going to come back to the problem of minimization, okay, how to minimize the logic expression in a later lecture. Okay, so this is described in a different chapter in your textbook. So I will come back to it later, okay, maybe next week. Okay, I will talk about it. But first, let us understand what's the meaning of minterm and max terms. Now, we need to define minterms and max terms because we need to obtain a logic expression, okay, for the function f. So what's the meaning of minterms and max terms? A minterm, okay, so I'm not going to answer here the question directly. So I'm not going to obtain a logic expression for the function f now. I will keep it until later, okay? So I will keep it for you to think about it. And let me define what do I mean by minterm and what do I mean by a max term. So the meaning of a minterm, it's an and term. Okay, so let me highlight here. And term. So this is the meaning of a minterm. And every variable must be present in this term, either in its true or complement form. Okay, for example, if I have a function f, which is a function of two variables x and y, there are four possible combinations of x and y, 0, 0, 0, 1, 1, 0, 1, 1. So the truth table of the function will have 4 entries. Now you can define an index that represents a decimal value for this combination. So 0, 0 will be defined as index 0. 0, 1 will be defined as index 1. 1, 0 will be defined as index 2. And 1, 1 will be defined by index 3. So therefore, if you have a function of two variables only, then it will have 4 entries in the truth table that are indexed from 0 to 3. Okay, you understand the meaning of the index here? So the index is nothing but a decimal value of the binary combination for the variable. If we had a function of 3 variables, x, y, z, let us say, then I will have 8 entries in the truth table, which are indexed from 0 to 7. So now I'm going to define the minterm. So the minterm here, minterm sub 0, this is for index 0. It is defined by this term, x prime, y prime. Now notice that when x is equal to 0, I'm going to put a prime, and y equal to 0, I'm going to put a prime. Okay, so this is how we are defining the minterm. Okay, for x is equal to 0 and y is equal to 1, minterm 1, notice that minterm is written as lowercase m. Okay, it's defined as x prime and y. So because x is equal to 0, we write x prime. Y is equal to 1, we write y. On the other hand, 1, 0, x is equal to 1, y equal to 0. This will be minterm sub 2. And it will be x, y prime, because x is equal to 1 and y equal to 0. And finally, for 1, 1, minterm sub 3 will be x and y. So this is how we define the minterms. Now, on the other hand, the max term, which is shown as a capital M means max term, it's an OR term. So the definition of a max term is an OR term. Every variable must be present, okay? Again, either it's true or complement form. But notice that the max term, if the value of the variable is equal to 0, we write it x. If the value of the variable is 1, we write it x prime. So the max term is simply the complement of the minterm. So the minterm here is x prime and y prime, whereas the max term is x or y. That's the max term. Now notice that x is equal to 0 and y equal to 0. And for this reason, we write it as x and y. We don't write to the prime, and it's an OR term, so it must be X or Y. Okay, so it's X or Y. So notice that the X here, it's in the true form, and Y is in the true form. When X is equal to 0 and Y equal to 1, this is max term 1 for index 1. So we write it here, max term 1. It is X or Y prime. Okay, so the Y prime because Y is equal to 1. Notice that the max term is always the complement of the minterm. So when you take the complement, okay, of X prime and Y, it will be X or Y prime. Okay, so just the max term by definition is the complement of the minterm. And finally, for minterm sub 3, which is equal to xy, the max term sub 3 will be x prime or y prime. Is this clear? So this is how we define the minterms and the max terms of a given function. Now, this is a function of 2 variables. So there are only 2 variables x, y. If we had 3 variables x, y, z, then we have 8 minterms and we can have 8 max terms. So in general, if you have n variables, if you have a function of n variables, there will be 2 to the power n entries in the truth table, and therefore you can have 2 to the power n minterms, and you can also have 2 to the power n max terms. Okay, so this is the definition of minterms and max terms. Now, why is this useful? Because you can systematically come up, okay, with an expression for a given function. Let me show you here minterms and max terms for a 3-variable function. If you have 3 variables, x, y, z, the index will be from 0 to 7. And there are 8 minterms, okay, which are indexed from 0 to 7, m0 to m7. Notice that minterm sub 0 is x prime, y prime, z prime. And finally, x7 here will be x, y, z. Now take anything here, for example, sorry. Let us take here, for example, at index 5. Index 5 is 1, 0, 1 in binary. So x is equal to 1, y equal to 0, and z is equal to 1. So minterm sub 5 will be x, y prime, z. Okay, because x is equal to 1, z is equal to 1, but y equal to 0. So we wrote here x and y prime because y equal to 0 and z. Notice that x, y prime, and z will evaluate to 1 when x is equal to 1, y equal to 0, and z is equal to 1. So it only evaluates to 1 when x, y, z are equal to 1, 0, 1. Okay. On the other hand, okay, the max term, okay, max term is capital M. Sub 5 will be x prime or y or z prime. It's an or term, whereas the minterm is an and term. Okay, this is one difference. Another difference is that notice that here we have x, here we have x prime. Here we have y prime, here I have or y. Here I have and z, here I have or z prime. So the max term will be 0 if x, y, z is equal to 1, 0, 1. So for this combination 1, 0, 1, the max term m sub 5, capital M sub 5, that max term will be equal to 0. So if this is equal to 1, x prime will be 0, y equal to 0. If z is equal to 1, z prime will be equal to 0. So this will give me the max term m sub 5 will give me 0 for this combination only. Okay. So remember that max term m sub I, capital M sub I, is the complement of minterm m sub I, and vice versa. The minterm m sub I is also the complement of max term capital M sub I. Any question about minterms and max terms? Do you understand this concept? It's a very simple concept.
I have a question.
تفضل محمد.
When do we choose minterm to be 1 and maxterm to be 0, or vice versa?
Now, this is the definition of minterm and max term. I'm going to show you how we can start using them to define, okay, expressions for a given function. Okay, so let us move on to the next slide and see how we can use minterms and max terms, okay, to write an expression for a given function. But this is by definition the meaning of minterm and the meaning of max term. So I really would like you at this point to understand the definition of minterm and max term and understand, okay, how we can write the minterm is an AND term, the maxterm is an OR term. I really would like you to understand this. And when do we write X? When do we write X prime? And similarly for Y and Y prime and Z prime. So it all depends here on the entry in the truth table, whether X is equal to 1 or 0, the same thing for Y, the same thing for Z. And remember that the max term is always the complement of the minterm and vice versa. Now, let us see how we can use this to write an expression. So the purpose of the index, as we have seen from the previous slide, is that we can designate a minterm and a max term with an index. So the index here is expressed as a binary number, while when we write the index, we write it in decimal, as we have seen in the previous slide. Okay, so m sub 0, m sub 1, up to m sub 7. Okay, so the index here is shown from 0 to 7. This is the index. So the purpose of the index is to tell me what is the binary combination of the variables, x, y, z. So 0 here means 0, 0, 0, because this is a function of 3 variables. And 7 will be 1, 1, 1. And 5 will be 1, 0, 1. So this is really the purpose of the index. It will tell me what is the binary combination of the input variables, x, y, and z. Now, here's the index from 0 to 7 only because I only have 3 variables. If I had, let us say, 4 variables, I will go from 0 to 15, and so on. So the more variables I have, I will have a range of index, or a range of indices, if you would like. Okay? Now, notice that for the minterm, when I write the variable, if the value of the variable, input variable, is not complemented, okay, so when I have 1 here, okay, it means that the variable is not complemented. And when the value of the variable is 0, it means that the variable is complemented. For the max term, it's just the opposite. If the input variable is 0, it means that the variable is not complemented. And if the input variable is 1, then the variable is complemented. Okay, this is what we have done in the previous slide. So if you noticed here, right, if you look at this slide, 1, 0, 1, notice that x is equal to 1, so we wrote here in the minterm, we wrote x. Whereas in the max term, we wrote x prime. Notice that y equal to 0, so in the minterm, we wrote y prime, because y equal to 0. Whereas in the max term, we wrote y. Okay, z is equal to 1, we wrote z in the minterm, and we wrote z prime in the max term. So this is how we define algebraically, okay, the minterm and the max term. So the minterm is an AND term. It is x and y prime and z, whereas the max term is an OR term. So we write it like, for example, max term 5 is x prime or y or z prime. So it's an OR term. So now, let us go back to the function that we have seen in the previous slide. So I had a function f, a function of 3 variables. Now, one way to describe the function, okay, so I need an expression for this function. So one way to write it is to write it as a sum of minterms. So this is known as a canonical form, okay? So the meaning of a canonical form, okay, so we have 2 canonical forms. Either we have a sum of minterms, okay, SOM, that's a canonical form, or we can have a product of max terms, which is explained in the next slide. So one way is to look at the ones of the function. So the function is 1. There are here 4 entries in the truth table in which the value of the function f is 1. So we focus on the entries, okay, of the function f, okay, the entries that have a value of 1. So these are called the ones of the function f. So we have 4 entries. So I'm going to look at these entries where the value of the function is defined to be 1. And I'm going to look at the corresponding index. So 0, 1, 0, this is index 2. So this is minterm 2. It will be x prime, y, z prime. 0, 1, 1, this is 3, index 3. So therefore, minterm sub 3 is x prime, y, z. I also have 1, 0, 1. This is minterm 5. X, y prime, z, and I have 1, 1, 1. This is minterm 7, which is x, y, z. So these are the ones of my function. So minterm sub 2 is equal to 1 only in one case, when x is equal to 0, y is equal to 1, and z is equal to 0. So we write it as x prime and y and z prime. It evaluates to 1 only in this case and 0 otherwise. Minterm sub 3 is going to evaluate to 1 when x is equal to 0, y is equal to 1, and z is equal to 1. So we write x prime and y and z, and so on. So now I can write my function. So we focus on the 1 entries, and I can write my function as minterm sub 2, or minterm sub 3, or minterm sub 5, or minterm sub 7. So we call it a sum of minterms. It's a sum of minterms. I can write it in sigma notation because it is sum. I can use the sigma notation, and I can list the indices here. This is minterm at index 2, at index 3, index 5, and index 7. So we can write it like this mathematically, okay, to describe it as a sum of these minterms. So these are the ones of the function at index 2, index 3, index 5, and index 7. And algebraically, I can write it like this. I can write it minterm sub 2 is x prime y z prime, or minterm sub 3 is x prime y z, or we have minterm sub 5 is x y prime z, or minterm sub 7 is x y z. So we can write it as a sum of minterms. Algebraically, I can write it as shown below. Okay, so we obtained from the truth table, we obtained directly an expression for the function f. Now this expression might not be minimal, okay, so it's not minimized. I'll come back to the problem of minimizing, okay, the expression for the function f later in another presentation. But at least we understand, okay, that this is an expression for the function f. Now we call this canonical form, and it is written as a sum of minterms. So you can take any function f, the truth table of any function f, and you can extract the ones of the function. You can write the minterms, and you can write it as a sum of minterms. Is this clear?
Doctor?
Fadal.
I have a question. Why didn't we write m0 as x prime, y prime, z prime, and
because
make
the value
f
of the function here, because the value of the function here for m0 is 0. So we don't count the zeros of the function. We only count the ones of the function. So when you want to write the function f as a sum of minterms, you focus on the ones of the function. So these are the ones of the function. So the function is 1 here, 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 and here. Okay. So we don't need the value of, we don't need m0 because the value of the function is 0. Okay. So
yes,
the
clear.
sum, so the sum of minterms, okay, so these minterms will be equal to 1, okay, okay, for these 4 cases only. And this is why we wrote it as a sum of minterms. So we focus on the 1 entries of the function. So this is why we have here, it is 1 for 0, 1, 0. So this is minterm sub 2. For 0, 1, 1, this is minterm 3. 1, 0, 1, it's minterm 5. And 1, 1, 1, it's minterm 7.
Doctor?
And we can write it mathematically like this in sigma notation. So these are the minterms, and we can write it algebraically using, we can write it algebraically, okay, as a sum of minterms.
Doctor, why we don't need 0? All zeros, just 1.
Now notice that the value of the function f is equal to 1 in these 4 cases. So when x is equal to 0, y is equal to 1, z is equal to 0, this will evaluate to 1. 1 or anything will give me 1. Notice that when x is equal to 0, y equal to 0, and z is equal to 0, the value of the function equal to 0. So if you substitute 0 here, 0, 0, 0, 0, 0, you will get 0.
I get it, yes. Thank you.
All right. So remember that the minterm is equal to 1 only in one case. So minterm 2 is, if you look at minterm 2, is equal to 1 only when x is equal to 0, y is equal to 1, and z is equal to 0. Notice that when x is equal to 0, x prime will be equal to 1, y will be equal to 1. When z is equal to 0, then z prime will be equal to 1. So you get 1 and 1 and 1 will give you 1. In all other cases, the value of minterm 2 is equal to 0. Okay? So therefore, we only focus on the minterms for where the value of the function is equal to 1. So we don't include all the minterms. We only include the minterms, okay, where the value of the function is equal to 1. Type. This is one way of writing an expression, okay, for the function f, and this is known as sum of minterms canonical form. There is another way, which is called product of Maxterms. But before that, let me give you more examples. Now, here I have a function f, which is a function of 4 variables. And it's written in sigma notation. Okay, it's the sum of these minterms, 2, 3, 6, 10, and 11. Now, notice that if I have a function of 4 variables, you can have 16 entries, which are indexed from 0 to 15, right, in the truth table. But only for the entry at index 2, 3, 6, 10, and 11, only for these 5 entries, the value of the function is equal to 1. It is 0 everywhere except for these 5 entries. Okay? This is by definition, okay, the function f. So I can draw a truth table. Okay, I can show all the 16 entries in the truth table, and I can show that the value of the function is equal to 1 only for index 2, 3, 6, 10, and 11. I can write it like this. Okay, so I can write it as a sum of minterms as minterm 2 or minterm 3 or minterm 6 or M10 or M11. Okay, now can you tell me algebraically what is M2? Algebraically, what is M2?
0, 0, 1, 0.
Yes, but algebraically, this is in binary 0, 0, 1, 0. But algebraically, to be what?
X bar, Y, Z bar.
It's actually A, B, C, D. Here are the names of the variables.
Okay. It's
A prime, B prime,
Yes.
C,
Yes.
D prime.
Exactly. What's M3?
A prime,
A
B
prime,
prime,
D prime.
C, D.
Yes. What's M6?
A prime, B, C, D prime.
Nice. M10?
A, B prime, C, D prime.
Excellent. M11, minterm 11?
A, B prime, C, D.
Okay. Excellent. So you got them. So now we obtained an expression for the function f, which is expressed as a sum of minterms. So we call this a sum of minterms canonical form. Okay. Now this expression is not really necessarily simplified, but at least we have an expression. It not be a minimal expression for the function f, but it's an expression for the function f. So there is no unique way to write an expression for the function f. There can be multiple expressions. Okay, so this is what we call the sum of minterm canonical form. Okay, here's another example. It's another function g. It's a function g, a function of 4 variables a, b, c, d. We only have 4 minterms. Minterm 0, 1, 2, 12, and 15. So can you give me the expression? The sum of minterm expression.
A prime, B prime, C prime, D prime.
Or what's
A
M1?
prime, B
A
prime,
prime,
C prime, and D.
صح. How about minterm 12?
A, B, C prime, D prime.
Nice. And what is minterm 15?
A prime.
A, B, C, D.
A, B, C, D.
Yes, follow
Nice.
A. Yes, yes.
Right, right. So it's A, B, C, D. So this is the algebraic expression. This is the algebraic expression because we are writing the variables. So the variable is either complemented, either there is a prime or there is no prime. So either it's in the complement form or it's in the true form. Okay, so A prime is complemented, whereas A is not complemented. It's in the true form. Okay. So we can take any function f or any function g, we can take its truth table, we can look at the ones of the function. These are the minterms. So we can look at their indices like 0, 1, 12, 15, and we can write it algebraically as a sum of minterms. Okay, is this clear? طيب, let me move on. As I said, this is not the only way, okay, to describe a function. Let us return back to our original function f, which is a function of 3 variables x, y, z that we have seen in the previous slide. Now, rather than focusing on the ones of the function, I'm going to focus on the zeros of the function. So here the function is 0, 0. Here it is 0, and this is 0. So I'm going to write here max term 0. This is max term 1, max term 4, and max term 6. Okay. Remember that the max term is just the complement of the minterm. It's an OR term. So here we write x or y or z. So when x, y, z are 0, 0, 0, we write x or y or z. We don't write the complements because it evaluates to 0 only in one case, when x is equal to 0, y equal to 0, and z equal to 0. It evaluates to 1 everywhere else. So max term 0, so the max term evaluates to 0 only for one entry. Max term 1 will be x or y or z prime because z is equal to 1. So it evaluates to 0 when x, y, z is equal to 0, 0, 1. That's max term 1. Max term 4 is going to evaluate 0 when x is equal to 1, y equal to 0, and z equal to 0. So we write it as x prime or y or z. And finally, max term 6, capital M6, okay, it's going to evaluate to 0 when x is equal to y, x is equal to 1, y is equal to 1, and z is equal to 0. So we write it as x prime or y prime or z. So now what we can do is that we can focus on the zeros entries. We can write the function f as a product of max terms. So it's max term 0 and max term 1 and max term 4 and max term 6. Okay, so we call it a product of max terms. I can write it in pi notation to indicate that these are max terms. So I use pi, and 0, 1, 4, 6 are the max terms, which are the zeros of the function. And I can write it algebraically. Okay, so I can write each max term between parentheses, and I can end these 4 max terms. So this is max term 0, which is x or y or z, and I have here max term 1, which is x or y or z prime, and here I have max term 4, which is x prime or y or z, and the last one will be max term 6, x prime or y prime or z. So this is another form, another expression for the same function f. So the same function f, we can write it as a sum of minterms, or we can write it as a product of max terms. Okay, and both of them are called canonical form. So in the case of the minterms, we focus on the 1 entries. In the case of the max terms, we focus on the 0 entries. Is this clear? So you can take the truth table of any function. If you want to focus on the 1 entries, you get the minterms. You can write it as a sum of minterms. If you would like to focus on the zeros of the function, you can obtain the max terms, and you can write it as a product of max terms. Okay.
So Doctor.
Doctor. Okay.
Yes, Abdurrahman.
Yes. So in short, I have a function. I don't know exactly what's the gates that cause the output. So I make equivalent gate by
Now,
using
notice
the
here
max
that I don't
term
have the circuit. I don't have the circuit. I only have the truth table. So from the truth table, we are trying to obtain an expression. And from this expression, we can implement the circuit diagram. Okay?
Yes.
So I'm starting from the truth table. I'm trying actually to write an expression from the truth table. I can write it either as a sum of minterms or a product of max terms. And once I have the expression, I can implement the circuit diagram.
Yes.
Okay? If I had the circuit diagram from the beginning, then we can just obtain the expressions directly from the circuit diagram. And once we have the expressions, we can obtain the truth table. Yani we can reverse this process. Okay. Any other question? Right. So now here are more examples. This is a function of 4 variables A, B, C, D. So we have 16 entries in the truth table, but we only have 3 max terms. So only 3 entries evaluate to 0. So the value of the function f is 0 for max term 1, for max term 3, and for max term 11. So I can write it as a product of max terms. Notice that max term, we always write it as capital M, whereas min term, we write it as lowercase m. So it's very important to use the proper case, okay, so that you don't really confuse anyone. Make sure that you write capital M when you are dealing with max terms. Now we can write it algebraically. So what's max term 1?
A or
Yes.
B or C or D prime.
Exactly. But you have to write it between parentheses.
Yes.
Because we are going to end it with max term 3 and max term 11. So what's max term 3?
A or B or C prime or D prime.
Excellent. And about max term 11?
A
11.
prime, A prime, B, C prime, D prime.
Where is the or?
Or between them.
Yeah, so you tell me again. So what's max term 11?
A prime, B, C prime.
Don't
D
say
prime.
B.
Or.
You say or B.
Or. Yeah. A
You have
prime
to write the plus.
or
Yes.
B or
Yes.
C prime or D prime.
Okay. So now we are correct. Okay, so you have to write the plus. The plus is the or operator. Okay, so this is now my function A, B, C, D, and it's written algebraically as the product of these 3 max terms. Okay, let us take another example. Function G, it has 3 max terms, max term 0, max term 5, and max term 13. Quickly, can you tell me what's algebraically the function G?
A or B or C or D.
Excellent. This is max term 0. And max term 5?
A or B prime or C or D prime.
Excellent. And we have max term 13.
A prime or B prime or C prime or D prime.
All of them prime?
No, the B is not prime.
Again, say it, max term 13.
D not prime.
B not prime
A
or C
prime.
not?
No,
C
C
not
not prime.
C not prime.
So it's A prime or
B
B
or
prime.
B prime or
or-
C or D prime.
Okay. So you got it now, okay? This is basically how we can write a function as a sum of, sorry, as a product of max terms. I made a mistake here. This is function not f, this is function g. So let me just here fix this mistake and write this as function g, right? It's not function f. Right. For some reason, actually now my computer system is slow. I'm waiting for it to respond now. PowerPoint. Okay. Right. So it's clear right now. Okay. So it's clear right now. Let us move on. Now we can easily convert between canonical forms. So there are 2 canonical forms. We have sum of minterms and we have product of max terms. So here I have the truth table of a function f, which is given by this column. Now notice that we have 5 ones. Okay, so this is minterm 0, this is minterm 2, minterm 3, minterm 5, minterm 7. And I have here, okay, 3 max terms, max term 1, max term here 4, and max term 6. So we have 5 ones and we have 3 zeros. Okay, so if the entry is a if the entry is a 1, it's a minterm. If the entry is a 0, it becomes a max term. So we have 2 choices. Either we can write it as a sum of minterms. So we can write it in sigma notation, sigma 0, 2, 3, 5, 7, or we can write it algebraically as M0 or M2 or M3 or M5 or M7. Or max terms. So we can write the same function f as max term 1 and max term 4 and max term 6. We can write in pi notation as 1, 4, 6. So these are the two choices. So if you know one, you can obtain the other one. So to convert from one canonical form to another, we interchange the symbols sigma and pi, and we list those numbers which are missing from the original form. So here, for example, we have 0, so we don't list 0. 1 is not present, so we list 1. We have 2, 3, we don't list them here. 4 is not present, so 4 is not a minterm, so it must be a max term. 5 is a minterm, it's not a max term. 6 is not a minterm, it must be a max term. And 7 is listed as a minterm. So either the value of the function is 1 or 0. If it is listed as a 1 in the truth table, then it is a minterm. If it's listed as a 0, it's a max term. Is this clear?
Doctor,
if
we choose max terms, everything the function will be 0, yes?
So the truth table of the function is defined by this column. Okay, yes. The column for the function f. So if it is a 1 entry, if there is a 1 under the function f, it means it is a minterm. If it is a 0, it means it's a max term.
But the function will be 0, so it does not have a value.
The function is defined by the truth table. The function has a value for each entry. So the value of the function is sometimes 1, sometimes 0. That's the truth table of the function.
Yes, okay.
Okay, is it clear?
Yes, thank you.
Okay. Now, to complement the function, if you have a function which is described by a truth table, the 1 becomes a 0 and the 0 becomes 1. So here's an example of a function f. These are the ones of the function. Okay, so we have 5 minterms, we have 3 max terms. So the 1 becomes a 0 and the 0 becomes a 1. Okay, so the function f here is a function of 3 variables. It is listed, so we can just list the minterms in the sigma notation, and we can also list the max terms in the pi notation. If you would like to obtain f prime, all what you have to do is just change the sigma into a pi, okay, as indicated here. So just use the pi notation rather than sigma notation. So all the minterms here become max terms for the function f prime, and all the max terms become minterms for the function f prime. Okay, so all what we have to do is to interchange the sigma. It becomes a pi, and the pi becomes a sigma. So this is how we obtain the complement of a function. So the ones of f become the zeros of f prime. So the minterms of f become the max terms of f prime, and the max terms of f become the minterms of f prime. Very simple, very easy, right? If you have any question, just interrupt me. So a summary here of minterms and max terms. There are 2 to the power n minterms and max terms, okay, for any Boolean function with n variables. So if the number of variables is n, you will have 2 to the power n entries in the truth table. Some of them will be 1s, some of them will be 0s. So the 1s are the minterms and the 0s are the max terms. So the minterms here correspond to the 1 entries in the truth table, and the max terms correspond to the 0 entries of the function. Okay, so any Boolean function can be expressed as a sum of minterms. This is one way to express it. We call it canonical form. Or we can also express it as a product of max terms. So there are 2 ways, either sum of minterms or product of max terms, and both of them are called canonical forms. These are not minimized. We can minimize them later on. So for any Boolean function, if you have the list of minterm indices, you can obtain the list of max terms, and vice versa. If I give you the list of max terms, you should be able to obtain the list of minterms. And if you take the complement, So the complement, you look here at the sum of minterms, it becomes a product of max terms and vice versa. Okay, all what you have to do is interchange the sigma with a pi, or if you have a pi, you interchange it with the sigma notation. Is this clear? So this is the summary of minterms and max terms. Before I talk about the next topic, let me just escape here. What I will do now, I'm going to create a new slide, okay, just as an empty slide. Okay, let me remove this, and I'm going to ask you a few questions. Can you see this empty? This is just an empty slide, a blank slide, okay? And let me use here my pen tool. So I'm going to write a function here, a function f. Okay, so this is my function f. Okay, so this function is a function of 3 variables, x, y, and z. Okay, can you see this?
Yes.
Type. I'm going to write it in sigma notation. I'm going to write here sigma. Okay, so these will be the minterms. Between parentheses, I'm going to list the minterms 1, let's see, 4, and 5. Now, these are the minterms of the function. What are the max terms of the function?
The rest of
0, 2,
0,
3,
2,
Yes.
and 3,
6 and 7.
and 6 and 7.
Yes. So we have to go all the way to 7. Right. So don't forget to write the pi notation. So the pi means max terms. Okay. So it will be 0. It will be 2. It will be 3. It will be 6. It will be 7. Right. So we have in total, we have 3 minterms and we have 5 mixed terms. We have 5 max terms. Okay. So 3 minterms and 5 max terms. Right. If I want to write algebraically the function f, I can write it as a sum of minterms. Notice that minterms we write it lowercase m1 or m5, sorry, m4 or m5, right?
right.
Right. Can you tell me algebraically what is m1? M1.
0, 0, 1, 0, 0, 0, 1.
No, algebraically, I know that 0, 0, 1.
X prime, Y prime, and Z.
So X prime, Y prime, Z. Okay, what's M4?
X, Y prime, Z prime.
Yes, X, Y prime, Z prime. Okay, so now what is M5?
X, Y prime, Z.
So we have X, Y prime, Z, right? You agree?
Yes. Yeah. Yes.
So I'm writing the function here as a sum of minterms. So I call it here, this is a canonical form. So this is actually sum of minterms canonical form. I can write the same function f differently. I can write it as a product of max terms. So what is max term 0? Algebraically.
X or Y or Z.
Excellent. X or Y or Z. So let me write it down here. X. Oops. It's really difficult to write on the screen because. Okay, so let me write X here. So this is X. So I have to write it like this: X or Y or Z. Excellent. Right. Next one. Now notice that it will be a product. So I have to write the max terms between parentheses. And of course, there is a dot in between. Okay, so it's a product of max terms. Second one, we have max term 2.
X,
y prime z.
Y prime or Z.
Yeah, you remember we have to say or, right? It's a
Yeah.
plus term, it's an or term. So it's actually X or Y prime or Z. Excellent. Next one, 3, max term 3.
X or y prime or z prime.
Or Z prime.
Yes. Excellent. We have still 6.
X prime or or y prime or z.
Nice. Last one, 7.
X prime or Y prime or Z prime.
Excellent. Are these for the same function f? Are we describing the same function f?
Yes.
Yani
Yes.
this expression and these expressions are the same?
Yes.
Yes.
They are.
Yeah.
We are describing exactly the same function f. Okay?
Okay.
So these are these are not really minimal expressions. I will show you later how we can minimize these. But these are two different expressions, okay, for the function f. The first one is the sum of minterms. The other one is a product of maxterms. Right, let me define g. G is also a function of 3 variables x, y, z. And I'm going to describe it here, okay, as a product of the following maxterms. I'm going to say here, let us say 5, 6, 7, okay? Right. So I can describe it. Of course, it is 5, 6, 7. I can list the minterms. Can I list the minterms here? In
Yes.
sigma notation, what are the minterms?
Yes.
0, 1, 2,
Continue.
3, 4.
Exactly. Right, that's it. 0, 1, 2, 3, 4. Right. If I would like to define a function h, which is equal to the function f and the function g, can you list them in terms for the function f and g? What are the minterms of
0,
f
1,
and g?
1 and 4.
Why?
Because that's what's in common with f and g.
Okay, so these are the 1 entries, right? So the 1 entries for the function f, they have to be common in f and g, right? So we look at the minterms, which are common in f and g. So only 1 and 4 are common, right?
Right.
That's it. Is 5 common?
Not in Minter.
Yeah, it's not common.
Neither
Okay.
neither in Maxter.
Yeah, so therefore only 1 and 4 are common in f and g. Of course, I can write it as a product of max terms. Can you tell me what are the max terms?
6 and 7.
Well, we have to start at 0 because anything which is not listed in the sigma notation must be a max term. So 0 is not listed.
2.
What else? 2.
3.
Yes.
5 and 6 and 7.
Right. So we have 6 max terms. We only have 2 min terms and we have 6 max terms. How about if I would like to get f or g? In sigma notation, what are the min terms of f or g?
0 to 7.
So what's the meaning here of the or?
One of them will be 1. It's okay.
Yes. So what are these?
0 to 5, I think. Yeah. 0, 1,
So we
2,
have
3.
0 to 5. Excellent. Thank you. So we're going to write 0, 1, 2, 3, 4. All of these exist in G, but also we have 5 that exist in F. Can I write this in as a product of max terms?
6 and
So
7.
what? Only 6 and 7 are the max terms of F or G. So we are defining here a new function, which is F or G. How about F prime? f prime is equal to what? In
We
sigma
interchange
notation. In sigma notation.
0, 2, 3, 6, and 7.
Yes, 0, 2, 3, 6, and 7. And in my pi notation?
1, 4, and
1,
5.
4, and 5.
Okay. So you see how this works, right? You understand how this works. Any question about this? Is this clear?
Yes, clear. Thank you.
Can I actually do f prime and g? F prime and g. What is f prime and g in sigma notation?
I think it's on.
Sigma and 6 and 7.
Here, right? We have
Six
f prime here.
2
So what
and
is
3.
6 and 7.
Well, we have to start at 0. 0 is common in f prime and g. This is
Yeah,
actually
0,
g
2,
here.
and 3.
So we have 0,
2 and
we have
3.
2, we have 3, right? So 0, 2, and 3 are common. 1 is not common, 4 is not common, 6 is not common, and 7 is not common, right? How about in pi notation?
1, 4, 5, 6, 7.
6 and 7.
Alas, okay. We got this part. طيب. Let us move on. Now, what we have seen is that we have seen the two canonical forms, sum of Minterms and product of Maxterms. We also have something which is called sum of products and products of sums. So the problem with the canonical forms is that they contain a large number of literals. That's the problem. So therefore, the function is not, the expression is not really minimized, and it contains a large number of literals. Because if you write a minterm or you write a maxterm, by definition, all the variables should appear in every minterm or every maxterm. Either it's a true form or complemented form. So there is another way to express Boolean functions, and this is called the standard form. Okay, so it's called the standard form. Let me use my highlighter. Okay, so we call this the standard form. It's not the canonical form, it's called the standard form. So remember these words because these are keywords, okay? So there are two standard forms. We have sum of products, or SOP. We call it sum of products. And also we have product of sums, which is called POS. Now the meaning of sum of products, it is you are ORing, okay, n terms. For example, here, if I have the function f1, it is xy prime or xz. Now notice that xy prime is not a minterm because the z does not appear. Xz is also not a minterm because the y does not appear. So we have here xy prime or xz. We call this a sum of products. So the terms here are called product terms, and we have the plus indicating the sum of products. The same thing here, f2 is a sum of products. Okay, so the first term is y, the second term is xy prime z. So here we have the function is a function of three variables. Notice that y is not a minterm. Okay, it is just a single variable, single literal. It's a term, but it's not a minterm. Okay. We also have product of sums. Okay, for example, you can write the function f3. This is another function, f3. It's x or z and x prime or y prime. So now we are ending or terms. So my terms here are or terms, and this is the end of or terms. So we call it a product because we have an end here of sums because my terms are or terms. Another example here is f4. Okay, it's also a product of sums. You can see that my first term here is just x, but my second term is x prime or y prime or z. So these are examples of sum of products and product of sums. Okay? Is this clear? Students, you understand this? So remember that the sum of products is not a sum of minterms, because not every term contains all the variables. Yani x, y prime does not contain z. X, z does not contain y. Okay? Here, y is a term. It does not really contain x or z. So some of these terms might be minterms, but not all of them. Sometimes there is no minterm, just terms. So these are more simplified expressions. So these are simplified expressions. We call them sum of products, or we can also have product of sums. So here, when I look at the term, it's an OR term, and it's not a max term because not all the variables exist. For example, here I have x or z. There is no y. Here I have x prime or y prime. There is no z. Okay, so these are not really max terms. These are just OR terms. So we call it product of sums because each term is an OR term, and basically my function is expressed as a product. Product means we are ending these OR terms. So these are standard forms. We call them standard forms. This is how we write expressions for Boolean expressions, for Boolean functions. Okay.
And will they always be in 2 terms or more than 2 terms? Is it possible to be more than 2 terms?
Yeah, sorry, I did not hear your question properly. Can you repeat, please?
Yes. Is it always the standard form in 2 terms, or it could be more than 2 terms?
No. The standard, okay, it does not have to be 2 terms. You can actually have any number of terms. Okay.
But not all of them are.
You can actually have, you can have 1 term, you can have 2, you can have 3. It does not really matter. But it has to be a sum of products. It has to be the sum of product terms. Okay, so we are ORing the n terms. In the case of the product of sums, again, you can have any number of terms. Okay, you can have 1, you can have 2, you can have 3. It does not really matter. But it has to be a product of sums.
And always there will be a term that's not, at least a term that's not
they don't really
a minterm or a max term.
No, they don't really have to be minterms or max terms. Okay.
Yeah.
So it's different actually from sum of minterms and product of max terms. Okay, this is the meaning of sum of products and product of sums. Here in this slide, okay, I'm showing the expression which is written in a standard form, as we have seen in the previous slide, and I'm drawing the circuit diagram. Yani, for example, for function f1, we have seen in the previous slide is f1 is xy prime or xz. So here I need an AND gate to AND x with y prime. I'm not showing an inverter here, but we need an inverter to invert y to obtain y prime. Here I need another AND gate to AND x with z. And then I take the OR of the outputs of these 2 AND gates. So you get here AND OR. This is the design of this circuit. So the first level will be AND gates. And my second level here is an OR gate. I'm not showing the inverters for simplicity. Here you can see that here F2, I have Y, or this is my OR gate. And I need to AND X with Y prime with Z. So notice that this AND gate is a 3-input AND gate. It has 3 inputs, X, Y prime, and Z. I'm not showing the inverter that will invert Y. Okay, so I'm assuming there is an inverter here, but it's not shown for simplicity. Okay, so again, it is AND OR implementation. We call it AND OR implementation because you AND first and then you OR. So this is in the case of sum of products. In the case of product of sums, we have here F3 and F4. Notice that in the case of F3, we have X or Z. So we are using here an OR gate. Notice that this is an OR gate here, right? To OR X or Z. And here I'm ORing X prime or Y prime, another OR gate here, okay? Again, I'm not showing the inverters for simplicity, but we need to invert X to get X prime, and we need to invert Y to obtain Y prime. Notice that the AND gate appears at the output, okay? So you take here the output of this OR gate and the output of the second OR gate, and then you AND them. So we call this an OR AND. So the first level is actually for the OR gates, and my second level here for the AND gate. So notice that it's called here. Okay, so this is OR AND. The same thing here, we are ORing and then we are ANDing. Now this term here, the first input to this AND gate is just the input X, but the second input is the output of the OR gate. It's X prime or Y prime or Z. Okay, so we call these, the first ones are called AND OR implementations for F1 and F2. We call them AND OR implementations because we AND first and then we OR. And the second ones, we call them OR AND implementations because we are ORing and then we AND. Is this clear?
Yes.
Okay.
Yes.
So what we need is that we need to minimize these expressions before we draw the circuit diagram, because if we minimize, we can reduce the number of literals and we can simplify the circuit. Okay, so this will be my next topic, is that I'm going to show to you, okay, a systematic way to simplify Boolean expressions. I'm going to show you how we can do this. Notice that we can use 3 input gates, AND gate, and here I have a 3 input OR gate. So you can actually have gates that have more than 2 inputs. You can actually have an AND gate with 3 inputs. You can even have 4 inputs. That is possible. Okay, so when we are designing logic circuits, we can have gates with 3 or more inputs. So some of these gates can have like 2 inputs, some of them can have 3 or even more. The inverter only has 1 input. What it does is that it takes its input and it's going to invert it. So if you have X, you get X prime. If you have Y, you get Y prime. Okay. So this is what we call a 2-level implementation. I call it 2-level. I have a level of AND followed by a level of the OR. Okay, you have here a level for the OR followed by a level for the AND. So we call it here OR AND. But this is 2-level. Okay, I'm not showing here the inverters. So really, even though the inverters exist in our circuit, but I'm not showing them for simplicity, and we not really count them as a level. Okay, so we count here the OR gates, the AND gates. So this is my first level, and this is my second level. I can even have more levels. Yani we can go, for example, to a 3-level implementation. Let us take a look at this function h. Okay, it is shown with this expression. Now, if you count the number of literals here, we have 6 literals. It is expressed as a sum of products. So we have 3 terms here. These are AND terms, and I'm ORing here. So the result will be 6 literals. But you can see that C is a common factor. I can take C. It's common here in CD or CE. So I can take C ended with D or E. If you count the number of literals, we have reduced it to 5 literals. However, this expression here, it's non-standard form. The first one is a standard form because it's written as a sum of products, whereas the second one is non-standard form. Notice that I'm ORing, then ending, then ORing again. So the second expression here, which is shown, it's not a sum of product, it's not a product of sums. So in fact, it will be a 3-level implementation. Let us take a look here. Okay, so for the first expression, I had AB or CD or CE. So I need 3 AND gates. The output of the first AND gate is AB, this is CD, this is CE, and then I need a 3-input OR gate to produce my output H. Okay, so I used here 3 AND gates, 3 2-input AND gates, and 1 3-input OR gate. Now that's a 2-level implementation. I have 1 level for the AND gates, and I have a second level for the OR gate. Now I call these AND gates at the same level because they can end in parallel. Okay, so the hardware is designed to work in parallel. So if you provide all of them inputs at the same time, they can produce their outputs at the same time. Okay, and then there is actually an OR gate. So the OR gate has to wait for the output of these AND gates before producing its final output H. Now you can have it differently. This is called a 3-level implementation. So I have here A and B, which is produced by this AND gate. I have D or E, which is produced by this OR gate. Then you end it with C. Then you OR, okay, with AB. Now notice that this is called a 3-level implementation. I have OR, I have AND, I have OR. Okay, so now it becomes 3 levels. Here I only had 2 levels, level for the AND and 1 level for the OR. Here I have OR, then AND, then OR. So this is a 3-level implementation. Okay, understand the difference between the two? Any questions about this? So this is my last slide in this presentation. Yes, Muhammad.
So which better to design
Well,
circuit? A 2-level or?
Well, it depends on if you would like to minimize the number of gates, or you would like to make the circuit to run faster. So there is always a trade-off between the speed and the cost of the circuit. I'll come back to it later. Okay, when I go into the details, we will see that these are 2 different implementations. Both are possible, but here the designer, okay, he has to select. Okay, do we care about reducing the cost of the circuit, or do we care more about the speed of the circuit? We'd like to make the circuit to be faster, and therefore it will have less delays. So in the case of the 2-level implementation, okay, the delay will be less because we have only 2 levels. In the case of the 3-level implementation, okay, we have 3 levels to worry about, and therefore this will increase the delay in the circuit. But sometimes if you use multiple levels, you can simplify the circuit, you can reduce the number of gates, and this can reduce the cost of the circuit. Okay?
Doctor, the 2 have the same number of gates. How can we minimize the
Well, in
number
this
of
example,
gates?
yes, in this example, but sometimes they will actually have different.
Okay.
Notice the difference is that this is a 3-input OR gate, whereas here this is a 2-input OR gate. And of course, if the 3-input OR gate is larger than the 2-input, it has a higher cost. Okay. So here we have 3 2-input AND gates. Here I have 2 2-input AND gates and 1 2-input OR gate. Here I have a 3-input OR, and this will have a 2-input OR. So this has slightly less cost because when you reduce the number of inputs to a gate from 3 to 2, you are reducing the cost of the gate itself. Maybe it's not clear now, okay, but I will clarify this point again. So we call this the fan-in. The fan-in is the number of inputs to a gate. If you increase the fan-in, then you are, in fact, increasing the cost of the gate. And also you are making the gate slower, okay? So there is a difference. This is a 3-input OR gate. This is a 2-input OR gate, okay? So even though the total number of gates is the same, the difference is in terms of the number of inputs to a gate. But in practice, in more complex situation, you can eliminate many gates by going to multiple level implementation. You can reduce, you can eliminate many gates, and you can have, okay, the reduction in the cost will be very clear. Any other question about this? So we are done with this presentation, okay, about Boolean algebra and logic gates. Let me do something here, okay? Let me insert, or let me just go back to the slide here. Okay, so what I would like to do is, again, I'm going to give you an example and see if we can work it out together, okay? So let me just here hide my camera. Let me take a function here, okay? So let me write it in standard form. So suppose I have a function here. So let me use my pen tool. Okay, so this is a function f. Can you see now my writing? No?
No.
Okay, I need to erase this. Okay. For some reason, the pen sometimes I cannot write if this pen is not working. So I have a function f. This is not going to work. It's really disaster sometimes to write with this tool. Okay, one more time. Come on, let us see if it works. For some reason, my pen tool is not recognized. Sometimes it causes problems.
Do you have OneNote, Doctor? It's work efficiently with the pens.
Even PowerPoint, see, I don't really want to switch now to another application. I just would like to write down with this tool. But for some reason, my mouse is actually creating a problem here. Sometimes it works. It just worked earlier. I did not really have any problem about it. طيب. I'm trying to just write anything on this PowerPoint presentation. ماشي. Let us see if I can write anything here. Maybe it's the battery. Anyways, let us not really waste our time on this. I wanted actually to show you an example using the pen tool. But oops, yeah, it's working, alhamdulillah. Okay, let us see. You can see it, right? So I'm going to write the function f. Yes, I'm going to write the function f. Okay, and this is a function of 3 variables, x, y, z. Okay. Now, suppose that the function f here is equal to x prime y, or it is y prime z. Now, this is clearly in standard form. It's a sum of products, right? It's a sum of products. So let us take this function, which is given by this expression, and let us obtain it. Let us rewrite it, okay, as a sum of minterms. Let us try to discover what are the minterms of this function. Do you have any idea how to do this? So I have a function which is given by this expression, and I would like to write it as a sum of minterms.
We write the truth table of it.
Yes, we can evaluate it with the truth table. Let us do that. So this is here the x, y, z, right? So this is my function f. So this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, right? So what's the value of the function f when x, y, z equal to 0, 0, 0? Evaluate. This is my
0.
function. Okay, 0, right?
0.
Because y equal to 0 is equal to 0. خلاص, we got 0. Next.
1.
It will be what? 0, 0, 1.
1.
Notice that y
1.
prime will be 1, z will be equal to 1, so therefore we got 1, right? 0, 1, 0.
0. No.
1.
1, 1.
1, 1.
1, because actually x prime will be equal to 1, and y equal to 1, we got 1, yes. 0, 1, 1.
1.
1.
1.
1.
Nice. Okay, 1, 0, 0.
0.
0.
Okay, so I will leave it now for you to tell me. Continue. Next, 1, 0, 1.
1.
1.
Good. Next.
0.
0.
Okay. Last one.
0.
Nice. Okay. So what are the minterms for this function f? In sigma notation. What are these?
1, 2, 3, and
1,
5.
2, 3, and 5.
Good. So I obtained the minterms from the expression. So I evaluated the expression using a truth table. Somebody is actually calling me, but I cannot answer them. Okay. So so now you can see that we have obtained the minterms for the function f. Next, what do I need to do next? Well, let us obtain now. Write it as a as a sum of minterms. I just need to actually have 1 minute. Let me show you how you can do it differently. I can take this term here, x prime. I can write it as x prime, y, and 1. But I can write it here z or z prime. Because z or z prime is evaluates to 1, right? And when you end it with 1, nothing changes. Or I have x is missing, so I'm going to write here x or x prime, and y prime and z. Do you agree?
Yes.
Do you agree? Do you see what I'm doing?
Yeah.
Z or
You're
z prime is
ending
equal
it
to
with
1.
one.
So x prime y and 1 is just x prime y. So by ending it with z or z prime, nothing changes. Here, by ending with x or x prime, nothing changes. Right?
Yes.
Let us expand. So this will be x prime y z, or I have x prime y z prime, or I have x y prime z, or I have x prime y prime z. You agree? So these two expressions are identical, right?
Yes.
Now this
Yes.
is minterm what? X prime y z.
M1.
How it's 1? 0, 1, 1 is what?
Sorry, it's
M3 or next one.
M2.
What is 0, 1, 0?
M2.
Yes. Next one.
M5.
Yes. Last one.
M1.
M1.
So these are the same minterms. So we obtain it algebraically. Can you see that?
Yes.
Can you see that? So from the sum of products, we can obtain a sum of minterms as indicated in this example. We can evaluate the expression using a truth table and look at the minterms. We can also expand it as we have done this, as we have done it here in this example, to obtain the minterms algebraically. Is this clear?
Yes.
Yes, it
So
is.
that's it. This is my last slide for today. I'm going to stop recording now.